So we'll have a quick revision of yesterday's class, and then we'll go to the remaining part of it to wind up this first part of our unit number 1. Now we'll be seeing a term called as dispersion operation, where dispersion is a procedure of mixing one material in another one. In majority of the cases, this activity is restricted to mixing solid particles in a liquid. The liquid concentration is more, solid concentration is less, and all the solids are to be presented in equal concentrations in the bulk of the volume of the liquid. Why do we require this is, suppose if you have a reaction between A and B, A is a gas and then B is a liquid. This will take place in presence of a catalyst. So how to start the process? Check the cleanliness of the reactor, close the bottom valve, add known quantities of liquid, that is B material, and then now you start the agitator. Now first add the catalyst, or what you do is, better if it is possible, pump nitrogen gas through the diplet. From the distributor plate, the gas comes out in the form of the bubbles, and these bubbles are not soluble in the water. So from the distributor plate, the bubbles are issued, they come out, they enter the bulk of the liquid, and they go up. So when the agitator is rotating, it will try to give a blow to the agitator, a bubble, and a bigger bubble may become smaller bubble, and like that these bubbles will rise up. As these bubbles are rising, then upward currents are created, and once your system is established, it has come to a steady state. Now you add the fine powders of the catalyst to the reactor slowly, so that the upward currents will prevent the settling of solids. We don't want solids to go to the bottom of the container because it is a catalyst. So it should be, now use the word dispersed. It should be present at all corners in equal concentrations in the bulk of the liquid. Then you can pump the gas, then the reaction takes place. But what is our aim? Our aim is to see that the solids are finely suspended entire in the liquid. Okay. And at this juncture, what happens is, let us see. In suspending solids, okay, the size and the surface area of the solid particles exposed to the liquid are fixed. First thing is, when we say catalyst, the size of the catalyst should be fixed. Let us go with solid catalyst. Size of the particle is 1 millimeter. When I say catalyst, let us assume that it is spherical in nature. So you have a spherical particle whose diameter is 1 millimeter. So you please calculate its surface area. Because why you are calculating surface area? Since the solid is dispersed in liquid, only the surface will be exposed to the liquid. So the most important thing is, what is the surface area which is exposed to the liquid is important. Because on this surface only, the gas will come, and then on the surface, it reacts with the liquid to form a product. So for us, a catalyst should be in a position to offer or to expose more to the liquid. So when the size of the particle is constant, and we assume that it is a sphere, then definitely the surface area is given by the formula 4 pi r square, which is also a fixed value. Volume of the sphere is also a fixed value. So hence, always a fixed area of the solid is exposed to the liquid. That is the meaning of the sentence. And where they are exposed, they are exposed in bulk of the liquid in which they are suspended. Even that volume is also constant. Means what? Once you fill the reactor with the liquid, you should not admit any other liquid. What is the liquid refers to here? That is the chemical B. I said A plus B in presence of a catalyst gives the product. A is a gas, B is a liquid. I am talking about this liquid. So by CPP you will be able to know how much amount of B is to be added. You add it first. So hence the volume remains constant. So hence this statement which are there here, that is, in suspending solids, the size and the surface area of the solid particles exposed to the liquid are fixed as in the total volume of the suspended solids. So how did we suspend it? In the solid particles, their area, volume of the liquid is same. We will consider this by means of a small example. Let us consider an example of suspending regular solids. What are regular solids? Regular solids are those solids whose sizes and shapes are clearly defined to us. Okay? So it is a sphere. When I say sphere, it is a regular particle in the liquid. Very good. Firstly, the solids are not dissolving in the liquid. If the solids are dissolving in the catalyst, if the catalyst is dissolving in the solvent, there is no question at all, no reaction takes place. So hence it should present on a medium and it should present separately. The diameter of the solid particles are fixed. If the diameter of the solid is d and assumed to be spherical, then the surface area of the sphere is pi d square. Now I said 4 pi r square. R I have converted to diameter. You know that diameter is equal to twice the radius, or radius is equal to diameter over 2. With that you get this formula. Let us also fix that number of solid particles in the liquid is 2000. One example I took it. You can take 100, you can take 50, depending upon the requirement, depending upon the amount of the catalyst required in the system, this number will come into the picture. Then the total surface area of the 2000 particles is 2000 into pi d square. The volume of each particle, that is volume of a sphere, is 4 by 3 pi r cube. It comes to pi by 6 d to the power of 3. Thus the total volume of solids is equal to 2000 into pi by 60. Now let the volume of the liquid is 2000 K. Now it is fixed, it is not changing. The diameter of the solid is fixed. Now this diameter of solid is fixed. Thus the surface area and the volumes are also fixed. And the volume is also liquid is fixed. Thus the surface area of the solids exposed to the liquid is also fixed, provided the solids are suspended in the liquid. If you are changing the flow currents, if the flow currents are disturbed, then immediately the solids will not rise, they will settle to the bottom of the container. So hence creation of the flow currents is very, very important. Then fixed, and thus the surface area, and then after suspending solids in the liquid volume is also fixed. Now next point. In the gas liquid or a liquid dispersion, gas liquid, I gave one example just now. An inert gas is pumped into a liquid. Okay, before we start the reaction, we are going to pump the nitrogen gas. Why nitrogen gas? Because nitrogen is inert gas, and then we wanted to create upward currents. So hence we use a gas liquid. Then liquid dispersions. For example, if a reaction is taking place between organic phase and inorganic phase, then of course we have to make an attempt to see that the liquid phase or the inorganic phase is dispersed in organic phase, or organic phase is dispersed in inorganic phase. That is very important. By contrast, the size of the bubbles or the drops on the total interfacial area between the dispersed and continuous phase vary with conditions and degree of agitation. Let us see one by one. In a gas liquid, we know. Liquid, we know. Dispersion operations, very good. What is our aim? We are supposed to disperse a gas in a liquid, or disperse an inorganic liquid in organic liquid, or disperse organic liquid in inorganic liquid. Then what happens? By contrast, the size of the bubbles. What is the bubbles here referring to? The size of the air bubbles, which are coming out from the distributor plate. Now remember, I will give 3 examples. First one is, you are supposed to pump nitrogen gas through air. How do you do it? You have a rotameter connected to the deflect. Already water is present. Start the agitator. Now you give connection to the cylinders, nitrogen cylinders. Then open the valve. You open, unfortunately, you open in such a manner that from the distributor plate also a jet of liquid is going out, jet of stream is going out. Means what? The flow rate is very high, the velocity is very high. Now you slowly reduce the valve. So when you close the valve, what will happen? Slowly the jet will become discontinuous, and then there is a chance that drops may come out from the distributor plate. Then only it is possible for creation of upward currents. If a jet will come, in the same area it goes out from top. No, we don't want that. We want to reduce the flow rate. And when you reduce the flow rate, bubbles will start coming out from the diplet, or at the end of the diplet we have kept a perforated plate. Through the perforated plate, the gas will be coming out. Now suppose if you further close it, what will happen? The gas may not have strength to come out because the drag force of the orifice plate is very high. So it may not overcome, so it accumulates inside. Okay, so it all depends upon the valve, how you are adjusting the valve, and by seeing into the system only, you should control the valve, and once you control the valve, don't disturb the valve position. Let it be as it is. Then only you will get bubbles coming out successfully from the distributor plates. Then after coming out, what will happen? They will enter the bulk of the liquid, and the bulk of the liquid is not quiescent, and it is not still, it is moving. Only flow currents are generated by means of the agitator, baffles, etc., etc. So now they start moving. They move in a direction which they are guided by or carried by the flow currents. Flow currents ఎలా ప్రవహిస్తుంటాయో వాటికి అనుకూలంగానే air bubbles వెళ్తాయి. But majority they try to go up because gas is not soluble in water. Gas always moves from bottom to top. So hence, sometimes what will happen, if the concentration of air bubbles is more, it may have a strength to change the direction of the flow current also, and dictate it. You also try to come along with us. Then an upward currents are formed. That is the dynamism which we are looking for this kind of reactions to take place. Then the total interfacial area between the dispersed phase and continuous phase. So what is interfacial area? For example, think of a air bubble inside a liquid. In a liquid, in a glass of liquid, an air bubble is present. So what will happen? There is a layer there. Inside the layer, air is present. External to the layer, we have air. So what I am concentrating? I am concentrating on the outer envelope of the air bubble. So when I concentrate on the outer envelope of the air bubble, inside air is present, outside water is present. So hence two molecules will exert some attractive forces or repulsive forces on the surface, which is called as interfacial tension. It is measured in Newton per meter. It is measured in Newton per meter. Very good. So the total interfacial area between dispersed phase and continuous. So when we have a number of bubbles, each and every bubbles will be having interfacial tension. Interfacial area they will have, and thus it facilitates the reaction to take place. Between dispersed phase is air bubble, continuous phase is water, with conditions and degree of agitation. What is the degree of agitation here? How you are going to move with RPM, and how you are going to create flow currents, because who are responsible for creating flow current? Your agitator is responsible for flow current, your baffles are responsible for the flow current, and types of the impellers, they will also decide. Suppose if you keep a propeller, then what will happen? You get axial current. If you keep a draft tube, you can control the flow of axial current. So like that, you fix the phenomenon, the procedure of creating the flow currents. The drops and the bubbles. Now drops here refers to presence of inorganic liquid drop in organic liquid, or the presence of organic liquid in the inorganic phase. And then bubbles are continuously coalescing and being redispersed. So if any bigger air bubble is there, the internal surface, the force exerted by the liquid on this may be high, so it breaks into small pieces, and then one large bubble may become 5 to 6 small bubbles. This procedure is called as coalescing. And they again after this they start moving in the bulk of the liquid, which is called as redispersed. Only first air bubble is dispersed, then after breaking, the small air bubbles will again get redispersed. In most of the gas dispersion operations, bubbles rise through the liquid pool and escape from the surface. Why? You know very well. Gas is not at all soluble in the liquid, and it comes from the top because its precipitate is less, and must be replaced by renewal. So continuously we are supposed to pump nitrogen to the system. In this dynamic situation, the volume of the dispersed phase held up in the liquid pool is also variable depending upon the rate of rise of bubbles and the volumetric flow rate. So you can fix this also. If you try to make an attempt of changing the volumetric flow rate of gas to the liquid, then definitely the number of air bubbles will also change. But what we want, I said already, take out the handle. Fix the position of the handle. Don't disturb it. Which handle I'm talking about? I'm talking about the valve. Okay. Then statistical averages are used to characterize the system since the hold up interfacial area, bubble diameter vary with time to time with position and then the vessel. Now, the most important thing is if the air bubble which is issued from the orifice, if it is a bigger one, so it will immediately take the blow of a impeller and then it becomes smaller bubbles. And these smaller bubbles, when they rise up, what will happen? Because of the differences in the velocities of different layers of the liquid, because of interfacial shear, again the sizes may be reduced. So this is a continuous process till the bubble goes out from the top of the liquid. But at an instant of time, we should have a specified number of air bubbles inside the liquid. Now, this is the theory part. Now let us see the mathematical part of it and how it is explained here. Characteristics of dispersed phase, in that we are supposed to find what will be the average size of the air bubble which is coming out from a particular system. How we are going to estimate it. This is what we require. Now, as I said, this is a small diagram. So the continuous phase is the liquid and the circle one is a gas bubble. Let volume of the liquid is equal to VL. So the entire liquid which is present here, VL. Let us assume that the gas bubble is a sphere. Thus, the volume of the gas bubble is 4 by 3 pi r cube. It will become pi by 6 dp raised to 3. And where dp is the diameter of the gas bubble. Very good. This is the formula for volume of a gas bubble. One gas bubble. But there are n number of gas bubbles. So hence volume of n number of gas bubbles is equal to simply multiply this n, which is the volume of each bubble. Then hold up. What is hold up? This is a big question. The fraction of gas in the system is called as hold up. So if hold up is high, more number of bubbles. Hold up is less, number of bubbles are less. So if the number of bubbles, you decide whether you want more number of bubbles, more amount of upward creation. So suspension will be very easy for us. Xi, total number of gas bubbles divided by volume of the liquid. So this is the total volume of the gas divided by VL. This gives the value of what's that? This gives the value of Xi. That is the hold up fraction. How this will tell us what is the fraction of gas or air bubbles inside the total volume of the liquid. This is the value. Next, the surface area of the sphere is equal to 4 pi r square, and since I don't use r, we use dp. So this will become pi dp whole square. The surface area of n number of gas bubbles is equal to simply multiply with n. Now, A is what? Interfacial area per unit volume. What is interfacial area? Yes, that is the total surface area of the sphere given by the formula pi d square, and n number of bubbles are there. So hence it is n, and per unit volume is Vl. So small a is equal to what's a pi dp whole square n by Vl. So now this is the equation number 2. So what I want is, I don't want VL in the equation number 1. I don't want VL in the equation number 2. So if you remove this, I get this equation. So finally I get diameter of the particle is equal to 6 xi by A. This is the unit. This is the value which I require. And remember, we have started our argument stating that the gas bubble is a sphere. It is a regular particle. Now suppose if it is irregular particles, bubbles of different diameter is there, we have to take average of all those diameters. And hence, now I say that the dp is called as d bar s, where d bar s is called as volume surface mean diameter or total mean diameter, and this d bar s is called, is again given by, mathematically identically it is given by 6 xi by A. So this is the formula. So what is the difference between this formula and this formula? 3 and 4. 3 is for regular particles, 4 is for irregular particles. That is the only logic behind it, nothing else. Now, gas dispersion, bubble behavior. In a constant liquid, that is still liquid, I added the liquid to the reactor. I have not started the agitator. I left it for 1 hour. So such kind of liquid is called a quiescent liquid, a single bubble. So now what you do? I start introducing one bubble one by one slowly. Let us see what happens. How does the bubble comes and what are the things which are necessary for it to come out in the form of a bubble. In a quiescent liquid, a single bubble is showing, that is a procedure of coming out from a orifice. Okay, if you see the distributor plate, at the end we are going to have a orifice. Okay, perforator plate. So each and perforator plate will have n number of orifices, and through this orifice only the gas has to come out. Very good. In a quiescent liquid, a single bubble is showing from a submerged, where, what do you mean submerged? The perforated plate is present inside the liquid, so hence it is submerged. So in a quiescent liquid, a single bubble issuing from a submerged circular orifice will be a sphere if the flow rate is small. Very good. If the flow rate is high, a jet of liquid will be coming out. If the flow rate is small, you will be having bubbles will be less. I just told you just now. If you try to increase the flow rate, the jet comes out. If you try to reduce, what will happen? Drop by drop, it will come out. What you want exactly? You want air bubbles to be formed, not a jet of liquid coming out from the orifice. So hence, it is you who will control the volumetric flow rate of a gas through the orifice plate, so that only slowly the drops will be coming out from the orifice plate. A sphere will be flow rate is small. Now let Fg is equal to gravitational force, and we know Fg is always given by the formula mg by gc, where m is equal to mass of the gas or the vapor, and rho v is the density of the gas or the vapor. So now you know mass, F is equal to mg by gc, you know the formula very well. So now I bring density. What is this density? Density of the gas or the vapor. Density is equal to mass per unit volume, you know. Therefore, volume is equal to V is equal to volume of the gas or the vapor. So now we will assume that the gas or the vapor is a spherical bubble. Then volume is equal to what? Pi by 6 dp raised to 3, where dp is the diameter of the gas bubble. Now Fg is equal to mg by gc. Now density is equal to mass per unit volume. Volume is equal, mass is equal to density into volume. So volume of the air bubble is equal to given by this. So hence what I made, sir? I made a process of converting F is equal to mg by gc to our equation. So in this equation, you will be having density of the air bubble or the gas, and then you have diameter of the gas bubble is there. Similarly, if you remove this density of the vapor and then keep the density of continuous phase, that is liquid, this formula will become Biome force. I told this in fluid mechanics also. The formula is same, but you should remove the densities. So if you now replace the density of vapor by the density of liquid, then you will have the Biome force. So here only the change is rho L. Rho L is what? Density of the liquid or the continuous phase. Now for the bubble to come out, Fb should be greater than Fg. So I have done this, and you have equation number 1. Then second point, the drag force is given by pi d naught into interfacial tension. What do you mean of interfacial tension? When the air bubble is coming out through that orifice, what will happen? The orifice exerts a drag force on the surface area of the air bubble. I repeat once again. When the air bubble is coming out from the distributor plate or from the orifice, what will happen? The orifice metal will be exhibiting a tension or a negative force on the surface area of the air bubble. That is called as interfacial tension. So unit is Newton per meter. Okay. So now Fd is given by pi d naught rho. What is d naught, sir? Diameter of the orifice which is present. Orifice means what? A small hole which is present inside the perforated plate. Very good. So now for issue of the air bubble, Fg minus Fd should be slightly greater than Fd. This is the condition. Okay. If Fd is more, it will not come out. If Fd is less, then it will come out. So mathematically, I will write it as Fg minus Fd, Fp minus Fg is equal to Ft. All the values are given to you here. So you make this formula, and ultimately I want the formula for dP. So if you have a formula for dP, you will have this one. Remember, sir, 6 is known to you. D naught is what, sir? That is the diameter of the orifice will be given to you in the specifications. What type of perforated plate you are inserting, that will be known to you. Rho, sigma, that is surface tension, the interfacial tension is also given to you. GC you know, G you know, rho L and rho B also you know. So with this formula, what did you achieve? You have found the diameter of the air bubble which is coming out into the bulk of the liquid, that you have found it. Then gas dispersion in agitation vessels. Now we will go for 2 or 3 empirical equations to wind up this topic. For large holdups, for low holdups, xi is less than 0.15. For a 6-bladed turbine impeller, the average bubble diameter is given by this. Remember, this is for what, sir? For a regular particle. For irregular particle, how to find, sir? We have to do empirical equations. We have to do experimental results only, and then we are supposed to come to the conclusion. So hence, d bar s is given by this formula. Now in this, sigma is known to you, gc is known to you, P is the power, V is the volume. So if you substitute all this, you get the value of ds. Similarly, if you want to find the value of A, that is our internal interfacial tension, this is the formula for it. Where V bar is here, superficial velocity or empty tower velocity, both are same. Okay, very good. Then UT is what? Bubbles rise velocity in the stagnant liquid. How the bubbles are coming out from bottom to the top of the container. Remember, sir, these are 2 empirical equations which are derived from means of experimental results only. So this is about the dispersion operations. Then the last one will be scalar. So before we go to the scalar, we have one more problem also in the scalar. We have, yeah. Can you see my screen?
No, sir.
You are not able to see my screen.
See the screen, sir.
You are able to see it now?
Yes, sir.
Yes, sir.
Okay, thank you. So now what we are seeing, now the last topic will be scalar. What is the meaning of scalar? For example, you are manufacturing a tablet for COVID cure. You got a data in grams of A, grams of B, all in the laboratory scale, small scale only you are going to do it. You conducted experiments in the laboratory with a total of 10 grams, and then you found the tablet, and then you were successful. Now you are going for large scale. So how to do this? Is there any standard procedure is available for us? That procedure is called as scalar. Developing a technology from laboratory to a large scale process is called as scalar. So generally what we do is, after conducting the experiments in the laboratory, first we will try to establish our result. What is the meaning of establishing our result? We have to reproduce our result for a number of times, so that ultimately we can know the process perfectly. That is the meaning of it. Then after that, what we do is, now suppose there is a reaction is there. So we know this is the equipment you are going to use it. So this equipment is a standard one, which have a motor, speed reducer. Means what? What is the meaning of speed reducer? How the original speed of the electrical motor is reduced to an RPM, which is required for you. In your problems, dear children, you have seen 90 RPM. But in reality, the RPM of the electrical motor will be 1500 RPM. So 1500 RPM has to reduce to 90 RPM. How we are going to do this? In the speed reducer, you are going to do this. Then you have a deplug, you have a baffles, you have all the type of the impeller. So here also you conduct an experiment. So I am using 6-bladed turbine 4-bladed turbine, I am using propeller, noted down the readings. I am using a propeller, push-pull type of propeller, noted down the readings. And I am using a draft tube instead of a baffle, note down the readings. So you perform a number of experiments, and ultimately what you are supposed to find, two things you are supposed to conclude. First one is the power consumption should be lowest, and the second one is what? The product is formed very fast. These are your two aims, because already you discovered the formula. Formula is there with you. You know what materials are to be added. So now once you know this, what will happen? You are supposed to design a system keeping two things in view. First thing is what? The power consumption should be less, and the time taken for the given product to form should be very less. Then only your model will be accepted. If not, we should go for the another model. So like that, we should do repeatedly experiments. And remember, all these repeated experiments should be documented. And whenever somebody is asking, you are supposed to conduct and then show to them. That is important. Then only you will get you go for the scale up or patent application, whatever. That is a different story. Then the second one is what? After conduct, where you conduct this? Again, you conduct this in your pilot plant. What is a pilot plant, sir? It is a little bit bigger version of your chemistry laboratory. In the chemistry laboratory, you will have conical flasks, beakers, etc., etc. There you conduct, you discover the process. But once that you discover the process, now you should increase the batch size. When you don't increase the batch size, we don't know exactly when you increase the size what happens. Can we get the same product or anything else? You should know. First, you are supposed to hunt it. For that purpose, you go to the pilot plant, slightly increasing the amount of the materials which you have used in the laboratory. So in the pilot plant also, you are supposed to conduct some experiments, and there also you should have some geometrical similarities. Now I use the word geometrical similarity. What is the meaning of geometric similarity? If you are conducting an experiment for 1 kL, 1000 liters. If you are conducting for 10 kL, 10,000 liters, the ratio should be set of what? Of the vessel. Then we say it is geometrically similar system. If not, no, it is not. So first step is what? You try to conclude, you conduct an experiment in an agitator which is shooting two things, which is solving your two problems. What are your two problems? Power consumption should be less, and second is what? The time taken for the product to form is also less. In that case, that is the standard model. Now, how you are going to go for the product? How you are going to go for the pilot plant? Pilot plant, the sizes are increasing. How do they increase? Yes, the same ratios which you are supposed to screen on the screen, you are supposed to follow. It's not like that. I like dA very much. I want to make dA equivalent to dt. You know what happens? The agitator will not rotate because it will instantly stuck the baffle and the motor will be jammed. No, sir. You are supposed to maintain the geometrical similarities inside the system. That is very important. So, conduct an experiment in the pilot plant, take 10 to 5 batches, conduct them, quantify your results, and once you are able to quantify your results, you are able to reproduce your result, then you go for again increasing the scaling. Like this, you go to the big chemical industry where you are going to manufacture materials in tons and tons. Then only your procedure or the story will be successful. And even in the production block also, you have installed 5 kL reactor. Initially, you will not full batch will not be given to you. You will go with 1/10th of a batch, because you are supposed to see whether there are any leaks are there, the dynamics of the process, how we are going to give the heat, how much we are supposed to give the heat, at what time you are supposed to take out the batches. All these things you are supposed to understand. So for that purpose, even if you go to a large scale industry also, before you start the process, you will be given an access to use only 1/10th of the original load. Once you get confidence, what is the meaning of confidence? By seeing the mirror, you get confidence? No. You have to know how much amount of product has to be formed by theoretically. If you are able to give same concentration, then of course you get the confidence. That is the meaning of it. And this conversion also should be scaled up. So from laboratory scale, how much you got it? From the large scale, how much you got it? This you are supposed to keep on noting down. So that once you go to the large scale, you will at least predict, yes, my conversion will be 97%. Now my aim is what? I should go for 100% conversion. That is your usual procedure. Then dynamic characteristics are also very important. Now in this type of agitator, what type of flow currents are generated? Because of these flow currents only you would achieve the task. What was the task? The task was to reduce the power consumption and then reduce the time taken for the given process. How it is possible? This box is not doing any magic, but this box creates a magic called as flow currents, which are established with respect to time. And in that flow currents only, the process of reaction, dissolution, maintenance, everything takes place, and then that will give your final product. So hence, dynamically, it should be similar. So whenever you are going from one reactor to second reactor, reactor to third reactor, when you are increasing the size, these kind of flow currents, established flow currents should be present in it. The meaning of the sentence is, in the prototype, if you are using 6-bladed turbine agitator, in the large scale, you don't have any rights to use a propeller type of agitator. Remember this. That is the meaning of the sentence. So whatever the similarities you are going to make in the, whatever you have used in the, pilot plant vessel, the same type you will be using in a large process vessel, but of course the ratios will be little bit bigger than one. And you know how we are going to increase the ratios as we like, we don't resist. In this slide, whatever the ratios are present, in the same way, same pattern, you are supposed to maintain the ratios even in the large process vessel also. Then, after this, what will be the parameter, kinematic parameter, which will be useful for me to maintain similarities? That is power consumption per unit volume. That is very important. Power consumption per unit volume. Initially, the size of the reactor is 1 liter. Power consumed is X kilowatts. X divided by 1 liter. What is the value? Take some value. This should be maintained in the throughout the scale-up process, from smaller one to bigger one. Whatever you use it, we are going to use this only. What is that one, sir? That is power consumed per unit volume is important. So in taking this kind of decisions, your experience and judgment plays a vital role. What do you mean of experience? You are in a chemical industry, you have joined a chemical industry initially, so directly they will not call you and they will say, please sit in the general manager's post. No, they will not tell you. But suppose as you work, you will be given training, you will start working. So after training the work, after working for some amount of time, depending upon your own interest, remember this, depending upon your own interest, because you go work and come back. I said that an operator is an operator for 10 years because he's a 10th class pass out. He never tried to focus his attention to other reactors or other processes. But you are not like that. You are having lot of knowledge. So you are supposed to draw your knowledge and then get the experience from the factory. So you should know how to start a reactor, how to continue the reactor. And after this reaction is over, what happens? Your time up? No. You are supposed to stay back and then learn where this material is going to the second stage. And in the second stage, what type of materials are involved? What are the unit processes which are involved? And what are the unit operations which are involved? And what are the plant utilities which are required for us? So all this data you learn it. And suddenly, till the process, till the final product is obtained, it may take approximately 1.5 days. So you stay back in the factory and then run and then see, observe it. Then you get some knowledge. So once you get the knowledge, what will happen? If tomorrow somebody asks you a question, what is going to happen today? Okay, suppose there are general managers, production operators are there who can also tell what will be the batch after 5 days. They will be able to tell it, predict it, provided you run the factory without any problem. So this much amount of experience, how do you get? Because of your committed interest in that particular industry. So you expend more amount of knowledge and then you expend more amount of time and you get more amount of the knowledge. And unfortunately, if an accident is taking place, if a problem is taking place, if a shutdown is taking place, first try to focus your attention why it was shut down, why the accident took place, what was the reason behind it. First, every time I used to say, whenever you are going to start a reactor, check the bottom wall of the reactor. If the bottom wall is not closed, if you pump the material will go to the second process. So what will happen? Without processing, the raw materials of first reactor go to second reactor. Everything is going to down. Your batch is destroyed. So hence, there is a procedural approach is there to run in a factory, which we all supposed to follow it. That is very important. So your experience, say for example, today today there was an accident was there because of some reasons. You were there at the factory and then you noted down. I got a small concept. See, yesterday the Andhra Pradesh government has kept in the website about the accident which took place at Vizag, LG Polymers. So if you are having any interest, you can read it. So you find that enormous amount of number of mistakes were committed by the human beings only. Human beings committed mistake, and because of this, there was a leak was there, and because of the leak, so many people lost their life, and so many problems are there for the government, for the people. All different kinds of things are happening. But suppose if you have followed the procedural approach, good manufacturing practice, if the step-by-step approach is in a systematic manner incorporating the safety, then of course that accident would not have taken place. So one thing, chemical industry is a good industry. Nobody will commit any mistake there. But if you commit a mistake because of your negligence or lack of knowledge, then that leads to a big accident. So that is very important. Now, if at all if any accident is taking place, then stay back and then do the auditing for it. What is the source of the accident? Why did it happen? And how can I prevent it? What are the measures I can take in future to prevent this accident? All these kinds of things, take a quantum of data and then keep it with you. And tomorrow such kind of situation arises, immediately you can rush to the place and then say that, yeah, you do this, you can prevent the accident. When you do this, how you got this? Because of your experience in the factory, you got it. And you can, when you have a good amount of experience in the factory, you can take a good judgment. When you take a good judgment, if it is good, then definitely the company will accept you, will accredit you, and then you can be playing a positive role in increasing the productivity of your farm, of your product. So this is the concept of scale up. Most important thing is what? When we are going from one size to another size to another size to another size, what we are keeping in common is only one thing. Power consumed by the electrical motor per unit volume of the processing material is important. This is the only thing which I am going to pick from first reactor to second reactor to third reactor. So this is about the scale-up theory part. We have only one problem in this particular section, scale-up. The final problem of our